So last week, we talked about some of the issues that people have noted over the years with null hypothesis significance testing. I'm not the kind of person who likes to just bring up problems and then just leave it hang. So I've come up with some ideas for potential solutions to ameliorating some of these issues. So welcome to part 2, how you can help science emerge victorious. All right, so by way of review, we've got 5 major objections that I've noted to NHST. The first is that we have this hybrid approach of Fisher and the Neyman Pearson approaches to statistical testing. Second problem is we've got this automatic 0.5 based decision criterion that we use no matter what the study is. And then that sort of connects with and feeds into 0.3, that we got this publication bias, this file drawer problem. And then 0.4, the straw man argument that demonstrating evidence against the null is not the same as supporting your particular alternative. And then the 5th is that you can basically cheat the test by getting a really, really big sample. All right, so what's the point of bringing up all this stuff? The point is that the logic of modern null hypothesis significance testing as it's presently practiced and taught is that we have a conceptually incoherent hodgepodge of the ideas of Sir R.A. Fisher and those of Neyman and Pearson. And the problem here is that these are 2 fundamentally incompatible approaches to research. And so if you want some more detail, you can see Gigerenzer's 2004 paper on this topic, where he explains why they're incompatible. And it is impossible to satisfy the conditions of both of these approaches simultaneously, and yet we, as a field, have tried. But even worse than that is that current practices encourage researchers to almost entirely ignore the Ziliak and McCloskey's point that we need to be concerned about practical impact. We need to be concerned about how much does it matter. And so, since their economists are coming at it with a certain perspective, and they argue that this practical significance needs to be compared against the potential costs, like last week I brought up the example of if I'm giving you a depression treatment, is it really worth all the money it's going to take and all the 12 weeks it's going to take for that program to improve your depression symptoms by 1 on the Beck Depression Inventory Scale? Probably not. So since when does a scientist care only about sampling precision, tested in an incoherent manner, as identified by Gigerenzer and others, rather than the practical impact of the effect that you've observed in your data? So I made this point before, it's worth reiterating, that there is no appropriate substitute for having a strong research design, clean manipulation if applicable, sometimes for obvious reasons for ethical or practical purposes. It's just impossible to actually manipulate things. Like if you're doing a study on men versus women and comparing them on some dimension, you obviously can't have random assignment to condition. So we can't always fulfill those. But when we can do an experimental manipulation, it's ideal to do that. And it's also helpful, I think, to have multiple replications and a logical explanation underpinning this effect. And I think there's too much focus on the statistical outcomes and not enough focus on this. So to buttress my point that science depends only on these characteristics and not on a statistical inference procedure, I've listed some enduring and important findings from the history of science. The discovery of the laws of thermodynamics didn't require anything like null hypothesis significance testing, nor did Darwin's discovery of evolution by natural selection, Mendel's discovery of genetic heritability, Crick and Watson's discovery of the double helix structure of DNA, Curie's discovery of X-rays, Van Leeuwenhoek's discovery of bacteria, Goldberger's discovery that pellagra was diet-induced rather than germ-induced, Pavlov's work on classical conditioning, or Piaget's theory of cognitive development in children. None of these things required p-values. So I think you get the picture. And that brings up the question, then why is it a necessary part of publishing science to do a t-test or an ANOVA or a correlation and get an associated p-value if these enduring, important, fundamental scientific discoveries didn't require it?
So, like, what are we supposed to do if we're not doing something that cool? Like, those are big, and that's kind of why. But we're not doing anything like that, so, like, what are...
Well,
I'm going to pretend my study is that important.
Maybe it is.
It's not. It's just not.
I mean, that's a good question, and unfortunately, I wish there were one single answer that I could just say, do this, voila. But unfortunately, that's not the case. It would be an oversimplification of reality to do that. I'm going to go through some advice regarding what I think is better statistical practice in the service of science, but ultimately it takes brains, it takes the human mind to judge, to evaluate, is this research design appropriate? Is this the best manipulation you could do? Is there something better? Is this an appropriate way to measure the thing you're concerned about for the dependent variable? And there's no statistical test I'm aware of that can answer questions like those. Yes.
Isn't that part of the problem too, though, that basically everything you have up there is qualitative research, meaning that they're just trying to describe a phenomenon or see if something existed, like in the discovery of X-rays. And most modern psychology is very much quantitative. We're looking for small differences between certain things and not just the existence of something.
Yeah, so that feeds into what I was saying, that it really depends on the research question. Sometimes you can have a more quantitative approach, like if you want to see how big is this effect, how does it compare to other studies, or to how does the effect of this medication compare to the effect of these existing medications that are already on the market. I want to show that mine's better. How can I do that? Well, I got to put numbers on it. And so it's helpful to have the quantitative approach to answer questions like that. You're absolutely right. But I think there seems to be this presumption among researchers that that quantitative approach is the only valid way to do it. Obviously not. Science has been done without using numbers. You can describe stuff very well and have something very important and interesting and fundamental to certain disciplines.
But you could come up with just as many examples where people qualitatively came up with bad science.
Oh, there's yeah.
So
I could come up with a list of the research in a variety of scientific disciplines where there's been outright fraud, made up data, and so forth. So this list was just to sort of emphasize that you don't necessarily have to have a small p-value in order to be doing important work. So this is a big enough deal that the American Statistical Association put out a statement about p-values a couple years ago, and I referenced it last week, but here we're going to get into a couple of the details of their observations from this paper. So their first principle p-values can indicate how incompatible the data are with a specified statistical model, and that's why it's important to have to test the assumption of normality. And I think they have the independent error assumption, and there's a bunch of assumptions that underlie all of these tests, and that's why they're important, because what the p-value indicates is how likely is this result to have occurred if all these characteristics of the null are true. And sometimes that's what you want to show, but it's important to keep that in mind. And number 3, scientific conclusions and business or policy decisions should not be based only on the p-value and whether it passes a particular threshold or a particular criteria. So that's not to say that it tells us nothing, but that's to say that it shouldn't be the basis for our decisions. And to a large degree in research practice today, it is. And statisticians are saying that's not the right way to do research. Their 5th point I talked about Ziliak and McCloskey in some detail last week. Well, this one, if you read this section, it reads very much like Ziliak and McCloskey. And considering that Ziliak was on this statistical committee that created this report, I guarantee this point number 5 was Ziliak. It says a p-value or statistical significance does not measure the size of an effect or the importance of a result. And then the last one I wanted to highlight from this paper is that by itself, a p-value does not provide a good measure of evidence regarding a model or a hypothesis. Again, it's not that p-values are completely useless, but they're limited in what they can tell us. And that's an important point to note, I think. So, who cares about all this academic garbage? Well, as we have discussed previously, there's a crisis of confidence in psychology research. And here I've linked just one of many examples of popular press articles based on that Open Science Collaboration paper from 2015, where they showed that only 30-some% of psychology studies successfully replicated. And so I think that's one of the big points, is not so much that the studies didn't replicate, which it's a debatable conclusion as to whether that percentage is an appropriate representation of psychology research. But this crisis of confidence, that I think that's the biggest takeaway from that study. But furthermore, there is a crisis of confidence also in biomedical research. And John Ioannidis really brought this out in a 2005 paper that he wrote. And it was provocatively titled, "Why Most Published Research Findings Are False." And that paper had a huge impact on biomedical research and even in other disciplines like psychology. And in a paper that it's kind of close to home for us psychologists, there may be a very good reason for this lack of confidence in biomedical research. There was a study in the New England Journal of Medicine, which is a very prestigious and well-regarded journal, that was talking about antidepressant trials and the fact that this selective publication, point number 3 that I talked about in my list of objections to NHST, the selective publication increases apparent efficacy of the drugs. So last week, Chris brought up meta-analysis, and rightfully so. But their point with this article is that the meta-analysis of the existing research on antidepressants would lead meta-analysts to overestimate the impact of these antidepressant drugs. So the conclusion that I take from all of this stuff is that we as a discipline have sold our collective soul for the appearance of quantitative rigor. Not actual quantitative rigor, mind you, the appearance of quantitative rigor. We have substituted mechanized pseudo-math for actual science. That is, we are relying on the statistical outcomes to guide our decisions when that is an inappropriate use of the statistical procedures. And so I think that the necessary outcome of this is the current replication crisis, and also in the dismissal of psychology by many natural scientists, physicists, chemists, astronomers, and so forth, that psychology is not a real science. And as much as it bugs me to hear that, you know, as I'm probably preaching to the choir here, we're all experimental scientists in this room, but as much as it bugs me to hear something like that, they're probably right, because by and large, psychologists and researchers in other social sciences have been misusing and lending too much weight to the statistical conclusions at the expense of experimental rigor, which is the more important factor. And so, if this is your reaction, like Macaulay Culkin in Home Alone, I've got some suggestions, I've got some recommendations about how to do this a little bit better, and also a brief explanation for why I recommend each of these approaches. So I've taken a made-up example from my preprint, from my manuscript that I submitted for publication. Turns out I'm going to have to thoroughly rework it, but in any case, I think the example can be useful. So in this example, I came up with a medication. I've developed medication X, and I want to see if it has an effect on cognitive function. And so I operationalized cognitive function in this made-up example by I have a list of 50 words, and people have 3 minutes or 5 minutes or something like that to memorize these 50 words. And then they've got another 3 minutes or 5 minutes or whatever it is to recall as many words from that list as they can. And so we've got, in one group, we've got people who have been taking this medication X for 6 weeks. And in the other group, we've got people who are in a waitlist control, and so they have been taking no such medication. And so you can see that the mean for the medication X group is high. So they recalled 9.7 words on average, and people who were in the waitlist control recalled only 7.7 words on average. So we've got a difference of almost 2 here. And you can also see for yourself, here's the SDs, they're similar. So there's a similar amount of variability in each group. That's useful to know. And then when you run the independent samples t-test, there were 30 people in each group. So you've got your 58 degrees of freedom. And then you get the t-value, and the associated p-value for that degrees of freedom is 0.02. And since I was just looking for a difference and not predicting it's going to improve or harm cognitive performance, I ran a two-tailed test. So this indicates that sampling error is not a good explanation for this average of 2-word difference. Furthermore, I used Cohen's d as a measure of effect size. So Cohen's d of 0.615 falls into the medium size category among Cohen's guidelines. And then I also ran a Bayesian independent samples t-test, and I'll talk about that a little bit more in a minute. But this Bayes factor of 2.697 indicates that the data are about 2.7 times more likely to have occurred under the alternative that medication X impacts cognitive performance than under the null, that there's no effect. And then I found the mean difference of 1.967, and I also found the confidence interval of the difference. So 95% CI indicates that colloquially speaking, the true population mean is likely somewhere between 0.3 and 3.6 in regards to the mean difference. So since that confidence interval excludes 0, we know that it's going to be significant at 0.05 level, and that medication X is yielding an increase. Bless you. And I also want to note these last two sentences here. So when I designed this study, I purposefully made it limited. I purposefully made it a little bit weak so that I could talk about this point. This only compares people who took medication X to people who took no medication at all. And so we don't know whether that mean difference is due in part or in full to a placebo effect or due to demand characteristics if this wasn't a double-blind study, and so forth. So there are other weaknesses to the design. So we can't necessarily isolate that, yes, people should take medication X if they want to improve their memory. And also, Dr. Anderson and I, and probably all of you, agree that it's important to have a good graph to represent. So instead of having to read through these paragraphs full of numbers, you can just look at the graph and see, oh, medication X, the mean is higher, so people recall more words. There's the confidence interval bars for both. So it's helpful to just have that in there to see. So I told you I'd give you an explanation of why. So first off, even though it seems like it's obvious that you should include means and SDs, I have seen papers where they did not do that. And so the first thing is you got to have the means and the SDs. So you can just have that raw, the look at the raw, here's the mean, here's the amount of variability, and we don't have any impact of sample size or anything else sort of getting in the way and making it tougher to interpret. And then that will help us to further interpret what's going on when we do the null hypothesis test and we get the p-value. And the p-value helps us rule out sampling error as an explanation for what's happening. And so a lot of the statistical reformers that I've read, when they talk about the limitations of null hypothesis significance testing over the past however many decades, a lot of them have advocated just abolishing NHST and not using it anymore. I think that's a bit of an overreaction, and it ignores the fact that sometimes NHST is useful. And so contrary to all these other reformers, I do not believe that it is going to be productive to abandon p-values. I think we just need to do a better job of putting in context what that p-value indicates. And I think we can do that by combining all this information when we do a study. So we've watched Jeff Cummings' new statistics video, and Cumming and Finch in 2001 published a big paper where they were advocating the new statistics, I believe for the first time. Was that 2001 paper? And it was all about confidence intervals. It was all about we should stop using p-values and NHST. We should use confidence intervals instead because they give more useful information about the effect that we're looking at, according to that argument. And it's a pretty compelling argument, I have to admit. But again, I don't think abandoning p-values is going to work real well. Because at one point in the videos with Cumming talking about the new statistics, he has a big cutout of a foam P, and he clutches it to his chest and he says, "We love our p-values, don't we?" Exactly. We've been doing NHST for so many decades that there's probably nobody alive who remembers when the field wasn't relying on this. And so telling people to just scrap it, I don't think that's going to fly. So confidence intervals are very helpful, and I think they should be used whenever applicable. But I don't think it's going to replace p-values or reporting means and SDs. And then you'll notice in my example that I used Cohen's D. Since effect sizes are immune to that effect that I described last week, where if you have a really, really big sample and even an infinitesimal non-zero effect, the effect size isn't going to be influenced by that, whereas the p-value will be. So effect size measures are important to sort of provide a check and balance against that p-value, so that you're not saying, oh, I got a significant effect, when your n was 57,000 and there's really nothing of interest going on, even if it is significant at the 0.05 level. And then a good graph or table, as I said, can really help to make the important summary information more salient, and it just helps the reader out. And so I think including all of these will be helpful. I also included the Bayes factor, which we've talked about the Bayesian tests a little bit before, but the Bayes factor is probably the easiest to understand statistical outcome that I have ever seen. So this is a table that is along the lines of Wetzel's and Wagenmakers in 2012. So the Bayes factor has been around for a long, long time. And back in 1961, Jeffrey, I think his name was Harold Jeffreys, a British statistician, advocated the use of the Bayes factor for scientific tests. And he came up with something similar, but his language was a little bit different, and according to Wetzel's and Wagenmakers, communicated a little bit too much certainty regarding the results, like if you have a weak effect. So this reflects Wetzel's and Wagenmakers' revision of Jeffrey's guidelines. And so a Bayes factor, so when you do a Bayesian test, typically your result is a BF10. There's also a BF01, which is the inverse, but I'll focus on the BF10 since that seems to be the default in how we report Bayesian tests. So a Bayes factor of 1 indicates no evidence for either hypothesis that you're testing. Now, the bigger it gets above 1, the stronger your evidence for what is generally termed the alternative hypothesis. I don't really like talking about alternative and null here, because one of the advantages of the Bayesian test is that it can compare competing hypotheses. So you don't necessarily have to have an alternative versus a null as we traditionally think of it. You can have 2 different alternative explanations. And if your experimental design allows it, you can determine the likelihood of one explanation or another explanation for some result. So there they call it the alternative and the null, but I prefer to talk about hypothesis 2 and hypothesis 1. Hypothesis 1 might be the null here, but it might not be. And so as this goes up, we've got stronger and stronger evidence for hypothesis 2, or the alternative. And then if the Bayes factor is below 1, down to the lower bound of 0, the smaller that gets, the stronger the evidence for hypothesis 1, or the null. And so I say this is so easy to interpret because if you have a BF of 10, that means the data are 10 times more likely to have occurred under hypothesis 2, or the alternative.
Are we taking questions and comments during this?
Sure, go for it.
All right. I guess I'd like to add my different interpretation here. So one of the things that's different about Bayesian analysis compared to null hypothesis testing is that null hypothesis testing, you're making an inference about the likelihood of data. More specific, the likelihood of an effect at least as big as the one you found in your data, assuming the null hypothesis is true. So you're assuming the hypothesis, you're not making inferences about the hypothesis, you're assuming the hypothesis, and making inference about, well, what data should you expect given that hypothesis. Bayes factor is different in that it works through the map and allows you to assess the likelihood of the hypothesis. Not just simply the likelihood of data, but the likelihood of one hypothesis relative to the other hypothesis. So Bayes factor 1,0 is a specific mathematics that allows you to assess the likelihood that the difference between means is non-zero. That's the one part. versus the difference between means being 0. That's the 0. So if you get a base factor of 2, that means that the hypothesis that the means are different is twice as likely than the hypothesis that the means are the same. So that number for the base factor is 2, 3, 0.5, whatever it is. It's about the relative likelihood of two different hypotheses.
Yes. Thank you, Dr. Anderson. So that was a good explanation of what we're doing here. And so I think that's useful in addition to the more typical tests that we do, in part because it's very easy to interpret, and in part because it's a better test to tell us what we typically want to know, which is how much more likely is this alternative versus another alternative. And so, I've said it before, and I'm going to say it again, that if you include all of this information, as I recommend, these are helpful and conclusive only if you have an appropriate design, a strong manipulation, and so back to Dr. Anderson's question from last week when he said how many replications does it take? Well, I don't think there's a good answer to that. But for practical purposes, I like the idea of, so you do your original study and you find, all right, now I have evidence. Preferably, I would like to see at least one direct replication of that, and then a different experiment to sort of conceptually replicate or extend your initial findings. If your direct replication attempt shows a similar pattern, even if it's weaker. And that will help us to this will help us to be more confident in our results. And so, as Dr. Anderson has talked about before at Psychonomics in 2016 and also in this forum before, he's presented the evidence that P, Cohen's d, and the Bayes factor are all monotonically related, and therefore, in principle, if you have one of these numbers, you can get the others. So that brings up the question, well, why shouldn't we just continue using P values like we've always been doing? And that's a legitimate question. But I think this replication crisis, or this crisis of confidence in research, indicates that something is very wrong here. And so at this point, I'm going to get into the probably most controversial part of my recommendations. And you may all disagree with me, and if so, that's completely fine, because I'm just throwing these ideas out here, and this is my current thinking on the matter. And I'm certainly open and welcoming of different ideas. And if I'm wrong and you can show it, please tell me. So, if you remember this stepwise sort of classification for Bayes factor values, like you got extreme evidence, very strong, strong, moderate, anecdotal, or none, I think it's reasonable to do the same thing with p-values. In fact, an argument could be made that, to some degree, we already see p-values that way. So, if you have a p-value of less than 0.01, that indicates overwhelming, very, very strong evidence that sampling error, or chance, or informal, is not a good explanation for our results. And so on, down to very strong, strong, limited, weak. And also, I'm going to point out this bottom part here. This is conditional upon a limited sample size of between 25 and 250. Now, mathematically sophisticated people would take issue here in that it is inappropriate to regard, like if you get a p-value of 0.01, that means something very different if you have a sample size of 250 versus if you have a sample size of 25 or 30. They indicate different effect sizes, different Cohen's d values or whatever. So that is a noted limitation of this proposal. But nonetheless, I think it is an improvement over current practice. And I will tell you why I think so. See, the problem with p-values has nothing to do with the statistical test. The problem is in how people interpret the result. And therefore, the issue is psychological rather than mathematical. And so we need a psychological solution to the problem. And so I've brought up before how this dichotomous classification of here's our criterion of 0.05, and if it's on this side, then you have a real effect and it's publishable. If it's on this side, it's not a real effect and it's not publishable. That decision rule comes from the Neyman Pearson approach to null hypothesis testing. And I think that causes problems because we are judged, for better or for worse, by how many publications we have. If I want to get hired at a prestigious university, I better have a publication list as long as my arm. And if nobody wants to publish my research, if my P is 0.06 or 0.07, then that would encourage me as a researcher to take what Simmons, Nelson, and Simonson have called researcher degrees of freedom. And this includes the optional stopping problem, where I'm going to collect data from 70 participants, and then that's it. And then I analyze my data, find a p-value of 0.072, and say, uh-oh, that's not good enough. That's not publishable. I better run some more participants. And then I just keep running participants until the p-value dips below 0.05, and then, boom, I'm done. Stop. That's cheating the alpha level that Neyman and Pearson, they said you got to set this alpha level, and then once you run your study, it is what it is. And so if you just keep running participants until you get below that alpha level, the alpha level is meaningless. Or another one would be to look at your data post hoc and say, well, this isn't quite significant, but if I drop these two participants, because they're outliers and so they're a little weird and possibly unrepresentative, I'll just drop those, and I might be able to come up with a great post hoc justification for doing so. But the fact is, I'm doing it so that I could get the p-value below 0.05. And so by using that stepwise interpretation procedure, that sort of de-emphasizes this dichotomous p-value based decision as the end or the outcome of the research process. And so that will encourage better mathematical integrity in our research by removing the tendency to judge the quality of my study based on the statistical outcome of my study as quantified by the p-value. And so I should note here, maybe you agree with me on all these points, maybe you don't. But even if we were to adopt everything that I'm recommending here today, including the stepwise interpretation of the p-value, so even if we do that, the temptation will remain to say, all right, now I'm going to set my criterion for Cohen's d here. I'm going to set my criterion for the Bayesian test here, and I'm going to set my criterion for p here, and so forth. And that temptation is always going to remain to let the statistics make the decision, make the inference for us. And we cannot do that. We have to judge the strength of the experimental design first and foremost. Because if that's strong, and then the evidence, statistically speaking, is weak, we've discovered that there's a weak effect. And so I had talked with Dr. Leventhal about this a little bit last week. And so this term is used in computer science. So whenever you create a program and you put in some sort of data in an appropriate format, the program is going to run through and do whatever it does, and then it's going to give you some output. And the program has no way of determining whether what you put in was random junk or whether it was something meaningful. It's going to give you the output nonetheless. All mathematical procedures work the same way. It doesn't know whether what you put in is of high quality or not. And so they use the term GIGO, garbage in, garbage out. And so since statistical procedures work the same way, that's why it takes the human mind, that's why it takes a brain to judge the quality of whether or not we're putting garbage into the statistical test in the first place. And so if you remember those old critics of null hypothesis testing, here's David Lycan writing in 1968 that statistical significance is perhaps the least important attribute of a good experiment. It is never sufficient for claiming that a theory has been usefully corroborated, a meaningful empirical fact has been established, or that a report ought to be published. And so I was hoping we'd have some time for discussion, but I took too long, and so unfortunately we don't have much time for discussion today. But if you would like to know more, I highly recommend that first one. I'll send around those links to the email list. The Ziliak and McCloskey 2009 article is pretty brief, pretty useful, and surprisingly interesting. And then a more academic article is Gigrenzer 2004. And these are both available on the internet. They're freely available. They're not paywalled, so you can be on campus, off campus. You can send it to your mother and have her read it. And so I think that's useful for the open science process. And so in that same spirit, my current manuscript, which I got to go back through and edit and chop up and fix, it's nonetheless available freely at the Sci Archive, which is a pretty new website where you can go upload your preprints, and so you can disseminate your ideas that way. And so since I started this talk last week with reference to the matrix, I will end it with one here today. Welcome to the real world.
So if our research is like methodologically sound, but our stats just like didn't turn out, would you recommend talking about this stuff in like our discussion, or?
This is at least one journal article unto itself. I don't know if it's necessarily going to be helpful, but it couldn't hurt your chances.
To be like, hey,
so
this is sound.
The statistics turned out, they turned out fine. They just turned out how they turned out. So if you didn't reach that P of 0.05 criterion, maybe the effect that you're studying just happens to be on the weaker side, which is fine. That happens a lot in psychology. I think it's a positive thing that you didn't just say, all right, I'm going to go back and collect more data and more data and more data until P dipped below 0.05, and then you can say, all right, see, it's publishable now. I think that's a corruption of the scientific process. So it couldn't hurt to bring this stuff up, to maybe run some additional statistics and say, all right, I've got evidence that this is a weak but legitimate effect. And I don't know if that's going to help you get published, but arguably it should, at least in my opinion.
But that is kind of the issue, isn't it?
That is the issue.
We can say, but generally,
Well, that actually reminds me of something that Gigrenzer talked about in his 2004 article. So in the 90s, I believe the name was Lofton, took over as editor of a major journal. I think it was one of the JEP journals. And so in his editorial, he said, I don't want to see people just mindlessly calculating p-values on autopilot. He also said that when people submitted their work, he said, you don't need a p-value here. Take this NHST procedure out. And authors insisted on keeping them in. So even though it's very easy for us to say, oh, well, it's the journal editor's fault that we're still stuck on this p-value thing, even in the cases where journal editors say, no, let's stop using this p-value stuff, people still wanted to keep it in because this is how we have been taught how to do statistics, and this is how we have been practicing statistics in research. And so I don't want to just put the blame on some other party and say, well, this is their fault. I'm trying to do better science. I think it's something that we as a field just need to work on all together.
No, I'm just thinking most journals do expect to be evaluated less than so you can convince the researchers that no, that's the wrong thing to do, but then they will publish.
Well, I'm hoping to convince everybody. So if enough people take notice of this, maybe this will actually affect a change. And I mean, for the past 20 years, discussion about this topic has really been accelerating. But I don't know if the OSC 2015 article was sort of the push we needed, but like I said, there's something really wrong in paradise here, and so I'm hopeful that as a field, all of us, not just the people in this room, not just researchers, but all of us, editors, researchers, graduate students, professors, undergraduate students, we need to rethink how we teach statistics. And so I'm thinking about this myself as I teach stats this semester, that I want to do more than just give lip service to the fact that there's more out there than just conducting NHST procedures and finding a p-value. But this needs to be introduced, I think, even at the undergraduate level, and then we need to teach as Gigerenzer calls it, a toolbox. We need to teach the statistical toolbox rather than just trying to use a hammer for everything. Sometimes a hammer is appropriate. Sometimes a wrench or a screwdriver is better suited for the task at hand. And so I think we need to educate people to begin with this principle, and then we need to practice it ourselves in research, and we need to get the editors on board with this so that they'll publish us.
That's my point. The editors, it's not the last step. It's, but if you're not going to be published,
Yeah.
You know, how are you going to?
Well, sometimes P will be less than 0.05. You just, even if you have a small study, if you have a really big effect, then that might get published anyway.
Yeah, I know, but you're kind of arguing against the values. That's the argument. And so, have you taken this to various editors and said, by the way, so you don't want people to do?
Well, I'm hoping to get a version of this into the published literature so they'll have more of a leg to stand on.
Where are you hoping to publish?
Anywhere where people can read it. Ideally something open access so that everybody can read it.
Right, well, that's what I mean. So if it's open access, it's not an established journal.
Well, some of them are, such as the Judgment and Decision Making. That's the Journal of the Society for Judgment and Decision Making. And it's, in fact, it's one of the top open access journals. But a lot of these open access things just cost a ton of money to the researcher, but not all of them do. JDM doesn't. Another one, Practical Assessment in Research and Education, I think it's called PAIR, is another free open access journal that's pretty well regarded and they have pretty good impact. So like I said, I've submitted this a couple times to a couple different places, some open access, some not, and based on the feedback I got, I'm going to have to really rework things, but hopefully this gets into the literature sooner rather than later. And so I'll have a leg to stand on so I can go to journal editors and say, hey, let's rethink this. And then also communicate to researchers as well. Hey, let's include a variety of statistical procedures so that you have a more comprehensive look at the data that you can then present to journal editors and say, hey, maybe P was 0.06, but look at all this other stuff. I've got a pretty reliable effect. Other questions, comments?
No, I just, so we're not the people who talk to.
No. So I have a couple of things. So one, there's been a lot of movement in this direction already. So there are journals that won't accept. Well, if you look at APA journals now, they want to de-emphasize null hypothesis systems. So they prefer confidence intervals and Bayes factors. However, despite what the journal policy is, the individual scientists reviewing the articles, I think, are still, they still demand it. So that's that. I actually published an article in the journal that Bob is editing on banned p-values, and it was a real pain. I mean, he didn't actually ban p-value, he didn't actually ban null hypothesis testing. He said, if you include it, so you can go ahead and include it in the manuscript, it can be there during the review process, but it will be taken out. Now, you wanted confidence intervals, but to me, it seemed like not very much different than the hypothesis, because to calculate your confidence interval, first you have to decide on an alpha, and you have to go through the t-test process at least far enough to get. I actually don't remember the formula. You have to figure out the t-value that would correspond to the alpha that you want to use. And the expectation is that that alpha will be 0.05. So you need that 0.05 as part of your formula calculating the confidence interval. And once you've got your confidence interval, you can very easily use it for null hypothesis testing. So, for example, I'll create a graph and so I have a 95% confidence interval. This suppose 0 in my graph right here. Okay, so if that's my 95% confidence interval around this mean, one of the things that tells me is that the mean is significantly greater than 0 because the confidence interval doesn't overlap to 0. So it became a matter of, instead of looking for p equals 0.5, we were looking for non-overlapping confidence intervals. So I don't think you have that at all. Number two, back then, graphing software wasn't that sophisticated, so I ended up having to draw my confidence intervals by hand. Not literally by hand, but like going into Microsoft Word. And so they're wrong. They're like lopsided. But I had to do that. I had to have wrong graphs in my article because we didn't want to scrap things. So that's my thinking on hypothesis. Now, yeah, I guess, Zach, I would assume that you'd have a lot of trouble publishing this because people have said this, and continuing to say it. As far as I can see, one thing I haven't seen people say before is to kind of put these verbal labels on value on p-values. There is a sense in which we kind of already have that, depending on what kind of research. So, if you're kind of an old school researcher and you do a lot of correlation matrices, you're often reporting a set of correlations in the table. And we have an asterisk beside some of the correlations.
Or two asterisks or three.
One asterisk if it's 0.5, 2 if it's at 0.01, 3 if it's at 0.01, whatever. And so, the more asterisks, the better. So, that's there, at least in that line of research. Bayes factor, I actually don't see why you need labels at all. I have 3. It tells me that the non-null hypothesis is 3 times more likely than the null hypothesis. Why do I need to attach it?
Yeah, that's an argument that I've seen that is a very good one. I think people find the verbal labels helpful, but then it introduces that sort of cutoff issue again. Instead of just having one cutoff, now we've got multiple cutoffs.
And then there's the issue of the Bayes factor. I mean, if you have a real effect, a non-null effect in the population, the more subjects you run, the bigger the Bayes factor. It's not different than food value.
Yeah, so your points are very well taken. I think there's going to be weaknesses of any test, and so my solution is to report a variety, and that way at least you can sort of ameliorate some of these weaknesses by having additional information in a different context. So I don't know if people will agree with that solution or not, but it's a discussion that's worth having. That's it.
I guess we're good. Thanks.
All right. Sorry, this went way over. My apologies.